All right, so we're going to talk about quantum numbers in this video. So basically, quantum mechanics is a set of complex mathematics that is used to describe the most probable location of an electron. All right, and so the key point here is that this location of the electron is based off of probability. All right, and this is complex equation that's used to come up with these numbers. Okay, now let's just say, for example, so I'm just coming up with a scenario that you're being chased by the cops and stuff like that. So the cops, they need to know four things to find the place that you're most probably going to be, all right? And most times people will think you're going to be at your house, right? And there's four things they need to know to figure out your address, all right? They need to know the state, the city, the street, and the street number, okay? And so this is the same idea with electrons. There are four things or four numbers we need to know, and we call these numbers quantum numbers, all right? And so the four numbers that we need to know to find the most probable area to find an electron, we need to know N, L, M sub L, and M sub S, all right? These are your four numbers. Now let's kind of talk about what each of these numbers are. N is just simply your energy level, okay? So what energy level is this in this electron is in? So you could kind of think about it in this sense. It's like what state, okay, in the United States, Georgia, New York, Wisconsin, whatever the case may be. Next one, L, tells us is what sub-level. Okay, and so when we're talking about sub-level, we could be talking about, hey, what city, okay? What city within the state, what sub-level within the energy level. When we talk about M sub L, we're asking basically what orbital or which orbital are we talking about? So what street name? All right, that's a way that you could kind of compare it. All right, so we know that the orbital is within sublevels, and we know sublevels is within energy levels, just much like we know that street names is within a city, and the city is within the state. And the last one, this one is going to be just a little bit different, all right? So M sub S basically talks about the direction of spin of the electron, okay? And in many sense, you could kind of think about this as the street number. So now we kind of pinpoint it to which electron are we talking about, or in the sense of, the cops are chasing you, we are pinpointing exactly which house, or where's your residence, okay? All right, so now these quantum numbers kind of follow series of rules, or there are possible values that each of these quantum numbers could follow, okay? So let's first talk about N. So N, okay, could be basically anything from 1 to infinity. Remember, N is just energy level, okay? So once again, we're just talking about the energy level here. So it could be energy level 1, energy level 2, energy level 6, energy level 8, energy level 10, whatever the case may be. It's an energy level. L, okay, it's possible values. So I'm just writing here, possible values. All right, for L is always from 0 to n minus 1. Okay, so hopefully that kind of makes sense. So let me just kind of give you some examples what I'm talking about here. So for example, if n is equal to 1, so here's just a couple examples. Okay, if n is equal to 1, L, the possible value for L, has to be 0. So once again, n is n minus 1. So for L, this has to be 0. Here's another example. Let's say n is equal to 2. Well, the possible values for L could be 0 or 1, okay? Yes, to say if n is equal to 4. Well, the possible values for L is 0, 1, and 2. So remember, L is always going from 0 to n minus 1. Let's get a big number here. Let's just say n is equal to 6, where the possible values for L is 0, 1, 2, 3, 4, and 5. So that's for L. Now let's talk about the possible values for M sub L. So the possible values from M sub L is always negative L to positive L. Okay, so M sub L is related to or is dependent on the values of L. Okay, and so let's look at a couple of examples here of what I'm talking about. So let's just say that if L is equal to, actually let me use a different color that way. Let's say if L is equal to 2. Well, what are the M sub L values? Well, for M sub L, it's negative 2, negative 1, 0, 1, and 2. Let's say if M sub L is 4, right? L is 4, I'm sorry. Then M sub L values will be negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. All right, so the values for M sub L is always, okay, negative L to positive L, okay? Now, and then when we have M sub S could really only have two different values. It's either plus half or negative half, okay? And so these are the possible values for, or these are the values in which that quantum numbers pretty much abide by, all right? And so the first thing you just got to make sure is that, you know, these numbers can coexist, can actually work together. So like here's an example. Let's just say if I gave you a set of quantum numbers that looks like this. All right, and this is usually the way how we always set up quantum numbers. Quantum numbers always go in the pattern of N, L, M sub L, M sub S. Okay, so now let's just look at these values. You see what we have. So we have N is 2, L is 3, M sub L is 1, and M sub S is 1/2, positive 1/2. Now, so let's go back to our possible values and see if this is correct or not. Well, N is 2. Well, we already know that N could be anywhere from 1 to infinity. So that value is okay. Let's look at L. Well, it shows you here that L is 3, right? Well, we know that the possible values for L is always 0 to N minus 1. Well, let's look back to N. Does this fit within the range? No. So we know that this is actually completely incorrect. And so this cannot work simply because this number is wrong. All right. Let's look through another example. So let's say we have 1, 0, 0, negative 1/2. Okay. So let's see if this actually works out. So once again, we know that this is N, this is L, this is M sub L, and this is M sub S. So we know that the value of N could be anywhere from 1 through infinity, so that works. We know that the value of L, all right, once again, has to be between 0 to N minus 1. Well, since N is 1, 1 minus 1 is 0, so this works. All right, so this checks out very well. What about this? Well, M sub L is always from negative L to positive L. Well, since L here is 0, this works. And then the M sub S is could be negative 1/2 or positive 1/2, and this works as well. So we know that this value, or this set of quantum numbers, is set. We're good. Now let's bring in the whole idea with electron address and quantum numbers together. And so hopefully this actually makes a little bit more sense. All right. So just like we were saying earlier, N, all right, is really just energy levels. okay? So it has the values going from 1 to infinity, all right? So depending on the energy levels, that's how far it pretty much would go. Well, we know L is our sublevels, okay? And when we're talking about things like electron configuration or electron address, we know that there's different sublevels. We have sublevel S, sublevel P, sublevel D, and sublevel F. Well, it also turns out that L, depending on the value, also correlates with these sublevels. So if L is 0, that means we're talking about sublevel S. If L is 1, then we're talking about sublevel P. If L is 2, then we're talking about sublevel D. And if L is 3, then we're talking about sublevel F. All right? And it correlates itself very well. Now, when we're looking at, so for example, if we have quantum set, let's just say 3, 2, -1, plus 1/2, all this is saying that this is the third energy level, all right? And L here is basically telling you that we're dealing with the D sublevel. Okay, so that's how you could that's how you will interpret this. Now, M sub L, if you recall that M sub L, its values is based off of -L to +L. And it talks about the orbitals, okay? Now, if you recall, going back, that we know that S, so let's list out our sublevel and the number of orbitals. All right, so we know that the S sublevel have 1 orbital. We know that the P sublevel has 3 orbitals. We know that the D sublevel has 5 orbitals. Oh, that's an ugly looking 5. Fix that. That's 5 orbitals. And we know that F sublevel has 7 orbitals. Okay, now let's look at the L values. So we know that the L value for S is 0. For P, it's 1. For D, it's 2. And for F, it's 3, right? Now let's look at the possible M sub L values and see how this correlates. So when L is 0, remember M sub L values is always from, and I'm going to write it above, it's always from -L to +L. So the M sub L values for 0 is 0, okay? The M sub L values for 1, all right, is from -1 to +1, so you have -1, 0, +1. M sub L values for 2 is -2, -1, 0, +1, +2. And M sub L values for when L is equal to 3 is -3, -2, -1, 0, +1, +2, +3. Okay, and so now when you're looking at this, and you could kind of compare this, the number of orbitals actually correlates to how many values you have. So since S has 1 orbital, you only have 1 possible M sub L value when L equals 0. Well, since the sublevel P has 3 orbitals, the L value is 1. We know that for the L value is 1, there's 3 possible values that give 1, 0, +1. If you notice, you have 3 orbitals and you have 3 possible values. For D, you have 5 orbitals, and when you have when the L value is 2, well, you have 5 possible M sub L values. And then for F, you have 7 orbitals. When the L value is 3, well, you have 7 possible M sub L values. So they really kind of correlate with one another, okay? And then last one, when we have M sub, well, still highlighter form, sorry. So when you have M sub S, remember, S sub S is just the spin of electron. All right, and so that all that's really showing is that if it's plus 1/2, we're saying that it's the electron spinning clockwise, or if it's negative 1/2, then the electron is spinning counterclockwise. So let's kind of put this whole thing together. How does that look like? All right, so let's just say we have quantum set number 2, 1, -1, -1/2. Okay, how does that look like? Well, here is just saying that this is energy level, so it's in the second energy level. All right, here is telling you what sublevel. Well, we know that L, all right, is telling you if it's a L equals 1, it is sublevel P. Okay. Well, we know that P has 3 orbitals, so I'm going to go ahead and just write it out with my 3 orbitals. Okay. And so it tells you here, it tells you which orbital we're talking about. Well, since it has 3 orbitals here, and then L is 1, the possible values for L is -1, 0, +1. The orbital in which the electron is in is actually in this orbital, okay? And then now you have -1/2, so what direction you going to draw the arrow? Down, all right? So basically, this is the way this looks like. We could easily kind of go the opposite direction as well. So let's just say I tell you, okay, well, here is a orbital diagram of this particular electron. What is the quantum numbers for this particular electron? All right, so what I would do, I would just automatically just label each of my orbitals. So this is -3, -2, -1, 0, +1, +2, +3. Okay, so let's kind of dissect this. This right here tells me my N. Okay, this tells me my L. This tells me my M sub L, and here will tell you my M sub S. So we could go ahead and put this together. My N in this case is, gotta make sure you put this back in pin mode. All right, my N is 4. My L, since it's F, L will be 3. All right, my M sub L, this is the orbital that is in, so it's +1. And then my M sub S, so since this is pointing downwards, it's -1/2. So this is my quantum number set. All right, so that's how you figure out quantum numbers.